about chemistry itself. It's a very old field, and by the way, this is a lot more for your general knowledge than for the exam. But chemistry is a really, really old field. Even before it was called chemistry, it was chemistry, right? You don't have to name something, to make it legal. But in any case, it's a very, very old field, and all you have to think about is, if you ever visit a museum and you look at the artwork there, then you will see how old some of the artwork is. Or if you ever heard of mummies that have been, mummified, and you'll think, okay, this is chemistry in action because it's been preserved for a long time. So there must have been chemistry back there, but they were not really called chemists, okay, back then. Eventually, the name came around to be called, anyone? Alchemy. Okay, so eventually the name came to be alchemy, which is more of an Arabic word. And then alchemy got changed into chemistry, okay, as such. So now we know chemistry as chemistry, all right? And chemistry is maybe 200, 300 years old formally as chemistry. So chemistry was just one field, chemistry by itself. Eventually what happened is it started branching out into different fields because there was so much going on. Okay, there was so much to do in chemistry, so the fields got separated out. Okay, so the first three fields of chemistry is physical, organic, and inorganic. These are the most fundamental three fields of chemistry. All right, and so physical chemistry, as the name states, is all about the physical nature, okay, of any substance, anything. So you study the physical properties of something. In organic chemistry, the middle one, you study anything that comes from nature, okay, and that's what the initial definition was. So anything that came from nature, like plants, animals, fungus, whatever it is, that was all considered to be organic. Later on, the definition changed for organic also. Organic is not just simply something that comes from nature. You can actually make organic molecules in the lab also, all right? And so organic was that initially, and then everything else that was not organic was inorganic, okay? Essentially what happens with organic, or what happened with organic, is that organic turned out to be the study of just one element, carbon. Okay? So not carbon just by itself, but carbon bonded with, say, hydrogen, oxygen, sulfur, whatever. Okay? But at least carbon had to be there in order for it to be organic, okay, in study. So, which means all the other elements that you see on the periodic table, those are considered to be inorganic then. Okay? So those are your three basic fields that you have for chemistry. The fourth one that came around in the last century was analytical chemistry. Analytical chemistry is about analysis. Okay, so if you want to study as to what the composition of this paper is, you would give it to an analytical chemist. Okay, so if there is a mixture, unknown sample that you want to test, you would do analysis on this. And this is the last field to be developed because of instrumentation. You need good instrumentation for this. And before that, there was no great instrumentation. In fact, you start wondering, these chemists were genius before that they could get anything done, okay? Because there was no way of analyzing the product or the reaction or anything. So it was really quite genius of them. But when analytical chemistry was developed, it was a lot of instrumentation. And so then you could analyze things very nicely, okay? And so analytical has become pervasive in all the chemistries now. So whether you do physical, organic, inorganic, it doesn't matter, you still have to do analytical, all right? So because it's analysis, and analysis is required in all the fields. My field is right here. I'm an organic chemist through and through, okay? All the way through, I'm an organic chemist, but I do have analytical also in me, okay, a little bit, because I had to do that in order to analyze my compound. So I have to learn instrumentation. So now there are so many instruments that you can't learn every single one of them, but at least you should know all of them. We good so far? Okay. What are you doing here in general chemistry? Okay. Where do you fall? Okay, in general, you see there's no general there. This is very, very specific, right? So there's no general chemistry. You fall under right here. with physical. So general chemistry courses are also known as baby P-Chem courses because a lot of it is physical chemistry, okay, that you do here. So whether it's GenChem 1 or 2, a lot of it is going to be physical chemistry, little bit is going to be inorganic chemistry, and if you touch organic, well, great, if you have time. If not, then you have the 1 year of organic after you finish general chemistry. Okay, so that's how these fields are for chemistry so far. Now there are so many more. The latest one that is offered as an undergraduate major is also biochemistry now. So if you take 1 or 2 more courses in biochemistry, then you have specialization in that as well. Okay, and biochemistry is the borderline between chemistry and biology. So DNA, RNA, proteins, enzymes, lipids, all of that. Okay, that falls in biochemistry. Anyone here, I remember not very many of you are pre-professionals or pre-meds, but the pre-meds pre-pharm, you all have to take biochemistry anyway, okay, at one point, because that's the borderline between chemistry and organic. Okay, so, or excuse me, biology. Now, there's even more specialization than that. That's your basic fundamental undergraduate chemistry courses, okay, that you take. So, after that, you can specialize even more when you get into master's or you do your PhD. You specialize more into, say, protein chemistry. In protein chemistry, you can be very specific into just enzymes, for example, okay, or even more specific as in digestive enzymes, or you're looking only at blood transport. That's all you're looking at, okay, or you could be even more specific and say, okay, well, now, you know, I'm just going to do nuclear medicine, that's it. Okay, and nuclear chemistry, nuclear medicine, that has to do with radioactivity. So again, that's a very small portion of this huge field, okay? Carbohydrate chemistry, very narrow field, all right? So it narrows and narrows more. I will be honest with you, very, very honest, because I have been through chemistry for so long, is that as you go on more and more into chemistry, you tend to enjoy it more, okay? At this level, it just seems very inundating. It's like, really, this is what chemistry is? But no, this is not really what chemistry is. Okay, chemistry is so much more than that. So the more you learn, the better it gets. Okay, so try to get through this and enjoy it so you can enjoy the later part also, okay, for chemistry. So that's the fundamental part. And by the way, another thing that I should mention to you, since I have been chemist for a long time and I read chemistry magazines and the job outlooks, it's one of the best fields to be there if you need a job. Okay, right away after undergraduate, you become employable right away. Okay, so it's one of the best fields to be in. Analytical chemists will hardly ever stay unemployable because you need them all the time, everywhere. Whether you're in a hospital or in a food industry or paint industry, everybody needs analytical chemists. Okay, so it's a very good field to go into. So I know I haven't convinced you in this 5-minute spiel, but eventually if you think about your career and you think about jobs, think about chemistry at one point, okay, or another, and give it a shot. Okay, so that's about chemistry. That's how it all got started. Now it's just a big, 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 huge field, and you have to study it right here. Okay, so all right, let's get into chemistry then. And one of the good things about chemistry is that you can't escape it. Okay, once you start thinking about your day, you have to think about the fact that you just cannot live without chemistry. The motto, logo, whatever for chemical industry is better living through chemistry, okay? And better living through chemistry, yes. How many of you like ironing clothes? Who does? Nobody does. You can thank chemists for that, okay? Because they are the ones who came up with the synthetic fabric so that you don't have to worry about ironing clothes anymore, okay? All this whole pharmaceutical industry, which it's a double-edged sword, the pharmaceutical industry, but all the medicines out there, something as simple as anisine, okay, or aspirin, that is the chemical thing that was developed by chemists, and you can't live without that, okay? So you start from your morning about how you brush your teeth and clean yourself, shampoo, soap, whatever it is that you do, okay, that's all chemistry. The ink that you're writing with, that's all chemistry. Right? So you have a lot to thank for, and especially I want you to thank chemists in your life whenever you open your phone. Whenever you look at your smartphone, I want you to thank a chemist, because if there were no chemicals, you would not have those beautiful colors, okay, in there. So thank a chemist for that, okay? But anyhow, so that's a little bit spiel about what chemistry was all about and how it's really everywhere. But then, let's talk about what scientists really do, okay, or what chemistry is all about. So, another heading for chemistry. So many headings for chemistry. Without looking at your notes, just look at me and tell me what you think about chemistry, or what you think chemistry is. Just raise your hand. I know you're dying to talk. So just raise your hand, and one person give me a little bit of a definition. Okay? Yes?
It's the creation of everything, creation of life, creation of
anything. So you're making something? Kind of. Yes. Okay. All right.
You're breaking it down.
Or you're breaking it down.
Yeah.
Opposite things. Okay. All right. So two things are going hand in hand. Okay. Very good. Anybody else? And this is your class participation points, which I keep a note of. It's all up here. So participate. Raise your hand. Let me know what you think about what chemistry is. Yes?
It's more like an understanding of everything, how everything functions, how everything fits in together, how everything connects with each other.
Okay.
Every reaction comes with an outcome. It's more of an understanding of how everything works.
Okay, so let's focus on that everything and that understanding, those two words there. Yes?
Chemistry is the study of matter.
Very simply said. Okay? Chemistry is the study of matter. All right? So that everything that you're talking about or creating something, that is all matter. Okay? So that's the basic definition, is that chemistry is the study of matter. Then you have to think about what is matter. How would you explain to somebody this is matter?
It's physical and chemical properties?
Yes. Chemical, not so, but physical, maybe. Yes.
It takes up room.
It takes up room, all right, and
Occupies the space.
that is, takes up room
Has a room.
and has weight. Okay, so two things there. And I hope you get used to my shorthand. So matter is anything that has volume and that has weight. That's how you define matter, okay? Which literally is everything in the universe. Okay, we don't study black holes. We don't. Yes, no black holes. We leave that to Stephen Hawking, okay? But other than that, we study pretty much everything, okay? So now regarding the chemical and physical properties that you said, yes. Okay, we will eventually get there, because yes, that's what matter all is. Okay, so we get there. So far so good? Okay, so then let's go ahead and classify matter. The first classification that I will do for you is the different phases of matter, which is gas, liquid, and solid. And these are things that you know already. I'm just putting them in perspective for you. Okay, so everybody knows that there are gases and everybody knows everything, but it's just a perspective. So gas, liquid, and solid, these are the three phases that we study, okay, at least in this world. Gases are when the molecules of anything are far apart. Okay, they're too far apart. They can take the shape of the container also, but they're still too far apart. All right, when you get to liquids, the molecules are getting closer to each other, and they take the shape of the container, and you can see that too. Okay, the only time you will see a gas is if it has color to it. If it doesn't have any color, you don't see it. Whatever is in front of you right now, you don't see it, you know it's there, okay, but you don't see it, all right? So the only time you see gas is if it's color, but liquid you will see all the time, okay, because it takes the shape of the container, the molecules are closer together. And then when it gets to the solid, the molecules are so close together that you can actually put them into a shape. All right, so you can bang it into a shape whatever you want, this, or a key, whatever you want. Okay, so that's how close they get. So these are the three phases, okay, of matter. And before I go too far, I just want to review one little thing here for you, is conversions, okay, of one thing to another, and you know all of these terms, okay, but we're going to put them into writing, okay, so that you can remember this, because this is something you're going to deal with in your lab, okay, all the time. So tell me, anyone, gas to liquid, that phase change is called?
Condensation.
Condensation. Going from liquid to solid is called? You know this.
Freezing.
Freezing. And if you've spoken once, then you can keep quiet for a while if you want to. We'll let the other people participate as well. So then going from liquid to solid would be?
Boiling? Melting?
Solid to liquid, I'm sorry. Solid to liquid?
Melting.
Melting. And then finally, liquid to gas would be?
Evaporation?
Evaporation. Boiling is slightly different than evaporation. Okay, boiling doesn't necessarily means that evaporation is occurring. It might occur. Okay, but it's a different process that in chemistry we kind of differentiate. All of these terms you already know. Okay, this is not something that's new for you, but I'm just putting it into perspective, because when you start communicating with me in your lab, in your reports, you should be as technical as possible. Okay, so you try to use technical terms wherever you can. There is one more phase change. Solid to gas, anyone? It's vapor. Sublimation. Sublimation. Heard that. It's vapor. Yes, it's vaporizing. Something is doing there. That process is called sublimation. And we don't encounter sublimation all the time, because whoever sees solid going into vapor. Okay, so that we don't encounter. But if you have been in the north, in the cold weather, anyone? Yes, one person, two person, three. Good, good. If you're there in the cold weather, it's really, really freezing at night, and then you see this white sheet on your windshield, okay, of water, and then suddenly the temperature changes, it will just go away. That's it. It will just turn into gas. Your windshield will not be wet at all. So which means it never went through the liquid process. Okay? Yeah.
So dry ice would be an example of something.
Very good. Dry ice would be the second example, okay, that you might encounter. And it depends. Again, not many people encounter dry ice, but anything that goes from solid to gas directly, that's called sublimation. And these processes, why they occur, how they occur, you're going to learn a lot more in GenChem2. Okay, there is a reason for everything. So why does something go from solid to gas is something that you will learn later on. Okay, because it is a very interesting phenomenon. Why does this happen? Regarding using these processes, you will do that the entire this semester. You will also do it next semester. So when you get into chemistry, you do things like this all the time. Okay, you do melting of solids, you do evaporation of solvents, and you also do sublimation. In fact, in 2 weeks, you have a lab called separation of mixtures, okay, in there. And separation of mixtures, you will see that you will be using some of these techniques there, okay? And please don't think that your lab is separate from the lecture, okay? Take all the things that you're learning from here and try to apply it in your lab, and you will see it's a lot more enjoyable, okay? And that's how we've designed our labs also, so they have that connection there for you, okay? So try to enjoy that as well. Okay, so matter, gas, liquid, solid, and then these are the processes. So these are the 3 phases of matter. Then matter, still going on with matter. A different classification. Matter can be classified as a substance or as a mixture. And if you have your chapter summary, you're most welcome to keep writing on that also, but otherwise take good notes, okay? Because until this part was all general knowledge, but now we're really into the stuff, okay? So which means I can ask you anything from here. So matter can be classified into a substance or a mixture. So a substance then is something that you can't differentiate, okay? Whether you have a single thing in there or 2 things in there, okay? You really can't. So substance can be further divided into 2 things, and that's called elements and compounds. And if you have trouble with my handwriting, let me know, because there is hardly any friction between the pen and the board. So I just go smoothly, okay? So if there's something that you don't get it, let me know. And a mixture can be classified into two: homogeneous and heterogeneous. No need to write too much because some of it is self-explanatory. Mixture, homogeneous. Homo means something that looks alike, all right? And so which means that anything that looks alike, you cannot tell whether that's a mixture or not. And that's what's really confusing between a mixture and a substance, because if I may borrow your water, if you don't mind, is you really can't tell whether you have one substance in here or if you have a mixture in here, okay? Because this is a nice homogeneous mixture. However, if I lift your cup up, then you can clearly tell it's a mixture, right? Okay, so this would be classified then as a heterogeneous mixture. And if there was ice in it, then definitely yes. Okay, it would be heterogeneous. There used to be. So then, yeah, and if water has ice and ice has melted, it becomes homogeneous, right? After being heterogeneous. So in any case, with heterogeneous, you can tell that you have more than one thing in there. With homogeneous, you can't tell, okay, that you have more than one thing in there. So again, the air in front of you right now, that would be classified as homogeneous, okay? Yeah.
This is a little bit ahead, but is every heterogeneous, does every single one have two phases? Because you can tell that it's heterogeneous.
No, heterogeneous can be also made of two solid things, for example, or two liquids. Okay, so suspensions, for example, if you open up a bottle of, well, I shouldn't say milk, of magnesia, and let me say salad dressing. Okay, so even if you just had oil and vinegar, that would be heterogeneous, okay, without any spices in it. So you can have, you know, two of the same phases and you can still have a mixture, okay, a heterogeneous mixture. So, but the key thing about homogeneous and heterogeneous is homogeneous, you cannot tell whether you have two things or not more, okay, but heterogeneous you can definitely tell. Between the substance over here, elements and compounds, elements are pure substances, they are just by themselves, they're not combined with anything, whereas compounds are combination of atoms, okay? So whatever you see here on the periodic table, and I know we still have to get used to the periodic table, but everything that you see on the periodic table, these are all considered to be elements, okay? They exist by themselves. The elements that you know so far would be simple things like gold, silver, iron, copper, okay? These are the things that you may have heard of before. Those are considered to be pure elements, okay? Substances or compounds over here. Compounds would be a combination of two elements. So for example, something like water, okay? Water is H2O, so that would be a compound. Sugar would be a compound. Salt would be a compound, okay? And don't worry, I will not give you any question that you cannot answer, okay? So I will give you things that you should be aware of, okay? I cannot imagine anyone not knowing that salt is an element or a compound. Am I right? Am I good? Okay, all right. So at least, you know, we should be aware of these things, and then you should be able to answer all these questions, okay? You should be able to classify. By the way, the website that I showed you with the green background, the one that was mine, the general chemistry, okay, on the webpage, you're most welcome to go there. I think all the worksheets are there now, okay? So you can start downloading from chapter 1. The first worksheet on there has to do with this topic. All right, all the matter classification and all of that. So, you know, start working on it. Again, don't get behind, okay? So 1 hour every day as we promised, so you can start working on that. Your homework on Blackboard is also available now, so you can start working on that also, okay? So whatever you learned today, try to do at least 5 or 6 problems or 10 problems of it that similar day, okay? So that way you will reinforce all of this. Okay, any questions in here? Okay, all right. Then there are a couple other things that I'll talk about which kind of get mishmashed into each other. Chemical properties and physical properties. Chemical change. And physical change. So these things are kind of all related, okay, to each other. This is still talking about matter. So some of you said already, when I was asking you questions about the fact that chemistry is a study of the chemical and physical properties, and yes, you are right. We do study chemical and physical properties. Okay, and remember physical chemistry, that was all the physical aspects, okay, of anything. So that would be a physical property. So what are physical properties like? It is, example would be, say, the color of a compound, the melting point of a compound, the boiling point of a compound, density of compounds. Are you not able to see? Is that?
I can just.
You can, okay,
The
yeah.
physical properties, things you see.
I'm sorry?
So physical properties is things you see.
Things that you see, things that you can measure also. Melting point, melting is something, a process that you can see, yes, solid going into liquid, but it is also something that you can measure, okay, and say that the melting point of, say, water or, you know, ice going into water is 0 degrees, okay, or something like that. So it's a measurable thing, so you can measure or not measure, okay, which is just observe. So those are physical properties. Chemical properties are very easy. It's the reaction, okay, of something. That's it. So if you mix two things together, and if something happens, then of course that's what it is. And really, when you start studying chemistry, that's what most people want to do. Okay, it's not like they want to look at this pen and say, oh, this is black, this is white, it's cylindrical. That's fine, except I really want to know what happens when I throw this in fire, right? Does it do anything, all right? And that's how chemistry gets started anyway, all right? Because you want to see what it does, all right? If there's any reaction to it. So that is chemical change then, okay? All right, so I'm going to give you some examples, so I'm going to ask you some questions and see if we can differentiate between the two. So tell me if it's a chemical property or if it is a physical property, okay? The fact that coal can burn in oxygen, chemical or physical? Chemical? Okay. And then if I take coal and I melt it into liquid coal? Physical. Physical? Are we okay with that? Okay, good. So what happened, what made you decide with coal going into liquid coal that, yes?
Well, the first one you were compounding it with oxygen,
Okay,
whereas the second one you were just finding its melting point.
very good. Okay, so which means that itself, its nature did not change. Okay, and that's an important part. Okay, and then that's exactly how you would differentiate, and that's what brings us to chemical change and physical change. All right, because chemical change is something that is not reversible. Physical change is something that is reversible. Okay, so for example, if I melted coal, which I don't know how I would do that, but if I melted coal and then I cooled it down again and it became solid again, that means I haven't really changed coal, right? The coal is still coal. It's almost like melting gold and then solidifying it also, okay, over water for that matter. Yeah.
Well, I think the book has that you would have to, if you wanted to change it back, you have to
Do another chemical, right, and I'm coming to that. So I was just talking about physical right now, okay? Yes, but for chemical change, when you go from chemical change, it is irreversible by itself, okay? So you literally have to do another chemical change in order to get back, okay, to your original thing. It's not like melting and freezing, okay, where it just takes a phase change, which is why we talk about phases over here, so you understand the difference between a phase change and a reaction, okay? All right, so another example over here. When I dissolve salt in water, is that a chemical change or is that a physical change? And you say that because somebody raised your hand who has never spoken before. Max. Your salt is still going to be there, okay? And this is a property that you have to remember, not the property that you can evaporate water, but the property that when you mix salt and water, you're dissolving it, okay? You're dissolving it. A lot of times when people don't know the right term, they say that the salt is turning into a liquid. Is it turning into a liquid? No, that's a phase change, okay? That's a phase change that requires a lot of heat or energy, okay, for that matter. But dissolving something may or may not require energy, all right? So it's an important distinction to make, all right? And the lab that you're going to do the separation of mixtures, by the way, that covers all of these things, okay, that we're talking about today. Matter, it covers all of this, okay? So try to remember all these things. Okay, so chemical change, irreversible, except by another chemical change, and physical change is definitely reversible. So you should be able to distinguish between the two things. Good so far? Let's come back to this chart again, okay, over here, because I want to use all of that and just add some more stuff here. So going from a mixture to a substance, do you think that would be a chemical or a physical change or separation? Going from a mixture, okay, yes?
Separation.
Separation, chemical or physical? Physical, okay. Did you say physical?
No.
Sorry, you said physical, okay.
It would have to be a chemistry because if you have sodium chloride and you want to change it back to an element.
But that's not a mixture. Sodium chloride would fall under the compound category, right? So somebody else was, yeah?
It would be salt water. Salt water would be a mixture instead of a substance.
And so when you're separating that, would that be chemical or physical? It would be physical?
Because you're just evaporating the water.
Evaporating the water, and evaporation is a physical process, right? Not a chemical process. Is everybody with me? Yes? Okay. And the easier way to think about it is, you know, having a salad that you did not make. So that's why somebody put olives in it and you don't like olives. And you got to take out the olives. Okay? And so that's what we're talking about. Okay? Is separating that kind of a mixture. So this one here is physical. Separation. Compound to element. Now that's going to be chemical. Very soon, in about 2 weeks or so, I'm going to learn your names. And maybe you'll like it, maybe you won't. I don't know. But then I can call out and thank the person who said all these things. Okay, so, and I can also call out and ask you to participate. And Max is the easiest to remember because Max is such a long name. Okay, that's why it's the easiest to remember. But anyhow, in any case, so the chemical change over here and the physical separation there. All right, so let's talk about physical separation because chemical separation is just a chemical reaction. That's all you have to do, okay, to separate things out. And as time goes on, you're going to learn about reactions. Okay, that's what chapter 3 and 4 are all about, is chemical reactions. Okay, so you will learn about it then. But physical separation is chapter 1. Okay, it's also your second lab. Okay, the separation of the mixture. So to separate things, what are the different processes that you can use, okay, to separate? So I just separated out the mushrooms or the olives or the tomatoes from the salad, right? No problem, all you gotta do is pick it out, right? So that's one kind of a separation possible. What other thing you can think of? Tell me if there's anything in your mind. Yes?
Boiling or condensation?
Boiling, so evaporation, right? Yeah, very good. So evaporation is one type of separation also. And that was the salt and sand kind of a separation. Okay, we can evaporate something off. Very good. Filtration? Yes? Okay. And filtration is a separation of what two phases? Solid and liquid. Solid and liquid. Okay? You can filter anything. You can also filter solid and gases also. But you should have the two different phases in there so you can separate them out. It's very hard to separate solid and solid. Okay, that's going to be hard to do. But otherwise, you can separate anything by filtration also. The easiest example to remember of filtration is when you boil pasta, spaghetti, whatever, and then you have to put it in a colander to get rid of the water. That is very simple filtration, okay, process. You're going to do filtration also in the lab. Okay, in 2 weeks' time when the lab is coming up. So you'll have filtration, you will have evaporation, you will have sublimation in there as well. Okay, so it's a really quite an interesting lab. I always tell my students in lab to enjoy the lab because you never get to do those things outside the lab. Okay, so once you're in there, you know, you enjoy it. You get results, you may get good results, bad results, it doesn't matter, but you'll never get to do things like that again. Okay, so try to enjoy the lab and don't worry so much about, you know, anything else in there. Okay, so that's the physical separation, filtration, and then there are some other things that are given here also. And as we keep going on, we will talk about more separation techniques also. How are we doing so far? Nothing so hard yet, right? Easy to do? I told you, your first exam is your marker, okay? Because all the stuff that we're doing here, a lot of it is common sense, a lot of it is something that you've done before, okay, in there. Okay, so I'm gonna go back just a little bit. Because one thing that I did not talk about in the beginning of the chapter was what we call the scientific process, okay, the scientific method. So let's talk about that. When you start doing science, there is a very specific way to do it. If you don't follow the same process, then maybe your results will be different. And that's why we have things that are called junk science, or pseudoscience, or political science. But okay, I'm sorry. All right, but in any case, all right, there has to be a process to this, and the process is there because science is very fact-based. Okay, so if you don't have your facts straight, then really you're not doing science. Okay, not only do you have to have your facts straight, if I take whatever work you have done and if I try to repeat that work, I should be able to get exactly the same results as you did. Okay, because if I cannot repeat your work, then that also is junk science because your work apparently is not reproducible. Okay, so science has to be done in a very methodical way so that you don't mess up something, so you have credibility, and then you can say, well, this is done in such a way. Okay, so that's why there is a scientific method. You all follow it one way or another. A lot of us do. We just don't realize that we're doing it. We do. Okay, follow it in some ways. There are people who go on in their lives without doing anything. Okay, but a lot of us do follow the scientific method. And the first aspect of a scientific method is observation. Simply said, if you don't have good observation skills, you are not a scientist. It's as simple as that. Okay, so even a person who is not a scientist, they can still have observation skills, and in my mind, that person is also a scientist. Okay, because you have to be able to observe and say, well, this is something that is unique that is happening over here. Okay, and that is what got all the discoveries started. At one point, the sun was going around the earth, and then suddenly everything changed, right? The sun became the center, right? And then we were going around it. So that is a result of observation, data collection, a lot of years of that work. Okay, and so observation is the first thing. Why does this happen? Okay, you observe something, it's happening every day, you know, so you have to be curious about, say, okay, well, this is going on. Why is it going on? And so you think about that, that is your observation. Then the second thing that you do is hypothesis. 3, 2. And your hypothesis is you try to come up with something to explain that observation. Okay, most simple thing I can say to you is you come on this campus from Congress, and at 9:15 there is a jam. You just can't get through. You just can't. Okay, so what's going on? For a person who's coming for the first time, like, what's going on? For some person who's not a student, okay, and they're just visiting the campus and they happen to come at 9:15. They're like, this is crazy. I can't get inside. Okay, it's taking me so long to get inside. Tomorrow they come in at 9:15. It's the same thing. So which means that they're observing something. Okay, that this is an observation. This is a pattern that's going on. So then what you do is you hypothesize. There must be something going on around 9:15 or 9:30 where this traffic jam is happening. Okay, and so that's your hypothesis. Okay, that you try to come up with an explanation for that. The next thing that you do is experimentation. And in experimentation, you try to figure out why this is happening. You collect data. You see if the data is reproducible. Okay, and then say, okay, well, I verified the fact that at 9:15 there's going to be a jam here. Why is that? 9:30 there is a class. Okay, how do you verify that it is the class time that is causing the 9:15 traffic jam? How would you do it?
10:45.
Come at 10:45. You can change your time, right? And see it come at a different time, or you could change the class time, right? And see if you change the class times, if two professors decided, well, I'm not here today, or they cancel the class and suddenly there's no traffic and something happens, okay? And so those kind of things, that's experimentation. You collect data. Experimentation is the biggest part of any science. This is where most people spend their time, okay? Yes?
That would only show a correlation when you have to ask each person individually why they're there.
Exactly. And then that's your experimentation setup. Okay, that you have to ask, you have to collect data, you have to see how many cars or what the people are there for. You're right. Okay? That's your experimentation setup. And that's what people look at. Okay, is that okay, this is justified or not? If you just asked 5 people, that's not enough data. Okay, that kind of a thing. So that's experimentation, and that is the longest part of anybody's work. Okay, it takes sometimes years and years, 20 years sometimes, to come up with something that is worth doing. The first 2 years of my PhD, it seems like it just went down the drain because I didn't do anything. Whatever I did not work. Whatever I did not work. Whatever I did, I would get to one point and then boom, the next time it wouldn't happen. So it's just like you keep working, and then you realize, okay, well, maybe I need to do another thing, okay? Maybe I need to change my project or something else. But in any case, that's experimentation, and it takes a long time, okay, to do this. So my hypothesis was completely rubbish then, okay, that I thought this would work. No, it did not work. So we had to change everything, okay, from then on. Anyhow, so once you do experimentation, after that, you come up with a theory. And a theory is pretty established. By the time you're coming to a theory, then it means you've established, you've done a lot of data collection, you have also published your work. In the experimentation part, there is also the publishing aspect where you have to share your data with your peers, and they decide whether it's valid or not, okay? Because they're going to repeat your experiments, and then they will decide, okay, whether this was worth it or not. Or they'll give you recommendations that maybe you need to collect this much more data in order for this to be valid. Okay, and so that is all in experimentation, but once that is all done and you've published papers in that, then you come up with a theory that this is what happens. Okay, and so that is pretty accepted. Anybody can challenge your theory, no problems. Okay, if you challenge a theory, you have to give your own theory then. Okay, and then prove it. Okay, and say, okay, I'm going to change the whole hypothesis, I'm going to do the experiment again and change the whole thing, which happens all the time. Because as you go on doing something, or as you go on living, things have changed a lot. Okay, you have a lot more information, you know a lot more, there's a lot more instrumentation, there are new techniques, and so you can study more in depth, and so you can change a theory. Okay, no problem. Nothing is written in stone. After a theory has been established, then you have what's called a law. And when a law is made, that's it. Law of gravity. It's done. It's there. Okay? That's it. Nobody can refute that. So, yeah.
And if it stays out of theory, it means it can't be proven. Like it's
No, it's proven. It is proven. If it stays as a theory, it means that you need a lot more data in order to go on to a law.
okay.
Okay, that's what it is. So it takes a long time for something to get to the law part of it. So it needs a lot more experimentation and a lot more theories. Because a theory can be a small picture of a big picture, just a small part.
So is that why the molecular theory of gases is a theory and not a law? Because
Yes.
we can't yet prove that gases are like
Yes.
smaller.
Yes. Well, it's not that we can't prove, but because there are some exceptions in there.
Okay.
That's why it's not a law. Okay, so when we get to gas and we'll learn about that, you will see that gases are theory only because we have exceptions.
Okay.
Yes. So that's how it works. So anyway, once you get to a law, it's the law, but again, you can challenge a law. Nobody says you can't challenge a law, but if you're going to challenge a law, you better be ready with your data, okay, to challenge that law. So be ready for it. And it happens all the time. I mean, this whole theory, and you will see as we go on, that, you know, at one time scientists thought that this was the good deal, and then suddenly everything changes, okay, for that. the whole reason why Einstein is because of his theory of relativity. Okay, and the whole completely, he just changed the entire picture, okay, of how we view things. Stephen Hawking, he changed the entire picture of how you view the world, how you view black holes. Not that we're going out there to see black holes, but it just changes your theory about, you know, or your view about, you know, how you look at universe. Max Planck, we're going to learn about him as well, and he's also one of those physicists who changed the entire view of everything. Okay, so people come along who are bright, smart, and they change everything. Okay, so nothing is set in stone, and I wish that one of you, two of you, three of you, more of you are those people who would change something like that, okay, and take us to the next level. That's what the scientific method is. So again, as you're going through the course, as you're learning to be a scientist, I urge you to think everything critically, okay, and not take everything at face value. All the drugs that are sold on TV, and yeah, admit it, we all watch TV, okay, and so when you see those ads in there, you know, you just have to take this pill and you will be slim and you will lose the weight exactly where you want it to be gone from. Or, you know, take this pill and you will grow hair. You know, it'll be just like when you were young. You know, you were 18 years old. It's going to be like that. What do? Do you just rush and call, like, yeah, I really want that pill? You know, do you do that, or do you look at the background?
You research first.
You research first. You have to do some research first. But then when you do research, what are you looking for?
The ingredients.
Ingredients of what you're studying, right? Of what's in there. What else are you looking for? The results, very good. And how much it's being tested on, right? Exactly, you want to see how much it's being tested on. The other thing, you want to know if it is approved by any agency or not. There are government agencies out there which help to at least make things safer, if not completely safe, but at least they're trying their best. Okay, FDA, EPA, they're all trying to make our lives easier. FDA is one of the biggest agencies out there for drugs and food, you know, and so if you see a drug is FDA approved, then maybe the chances are okay, it's better than something that is not FDA approved, okay? So all the vitamin supplements that you see in Walgreens, in CVS, a lot of those are not tested. People just spend all that money on the vitamins without knowing whether they are going to do that result or not, okay? Whether they have that much vitamin B12 or B6 or C in there or not. It says 1,000 mg, but who checked? Nobody checked. Okay, and so as you become scientists, as you become those critical thinkers, I don't want you to take anything at face value. You know, you have to think about it, you have to analyze it, and then decide. Okay, so you should be able to differentiate between junk science and good science. Okay, and then I urge you to do good science. Okay, don't do junk science, because we have enough of those out there. Okay, so become a good scientist. How are we doing? Good? Questions? Okay, good.